Alright, so let's talk about carboxylic acid derivatives. And all of them have the same general structure here of some type of alkane chain bounded to a carbonyl with a heteroatom molecule or a heteroatom itself. And one of the things I think notes that we can make about this, obviously I'm not even going to write this out, but this is sp2 hybridized carbon. It is trigonal planar, it's flat. We've already discussed a lot of carbonyl compounds, and this really isn't much of an exception. We've even done a lot of reactions with these species. But one of the things that we haven't talked about is really just, I guess, in terms of structure and bonding, the identity of Z. So Z can be two really good things, and this is going to make sense with reactivity later on. This can be a really good leaving group, or this can be a base. And these two things can determine the reactivity of our species. For example, and it's not just the reactivity, it determines the overall structure of our molecules. So let's just talk about this. So as for all the derivatives that I'm going to list in the beginning, as basicity increases, then the stability of your molecule increases. So this has a direct relationship between basicity and stability. Stability of the overall molecule. Also, something that I really wanted to note this, as this becomes more basic, so as things become more basic, the more that minor resonance structures, the more basic, I guess, the identity of Z is. I know this is really abstract, but I promise you it'll make sense. The more basic Z is, the more the minor resonance structure tends to be. So the minor, I'm just going to write RS for resonance structure or resonance hybrid, contributes to the hybrid. So I guess I'll just kind of try to pan out an example of this. When we start talking about other compounds, I'll just use an amide as an example of this, and then compare that with an acid chloride. So here we have an amide, and it doesn't matter what the identity of those hydrogens is, it can be an R group. And then I'm going to compare that with an acid chloride. I'm going to fit this in here. It's not going to take too much time. So which one of these is obviously more basic as their own? And what I mean by that is in the, I guess, taken to the extreme, the ionized form. So obviously NH2 is a stronger base than chlorine, an exponentially stronger base than chlorine. So which one of these molecules is more stable? This is going to be more stable. The amide is going to be more stable than your acid chloride. If I were to draw this and explain what I mean by this in terms of contributing to the resonance hybrid, move this in here. If I move these electrons in here and move an oxygen up there, just in terms of the hybrid here, this is so, I guess, kind of abstract thought here. This contributes there. The more stable it is. So this lone pair on this NH on the amine of the amine of the amide. God, I can't talk today. But this lone pair is almost like in a conjugated system. This is not a basic. This is an unreactive lone pair, which is totally different from if it were, say, ammonia. Ammonia is a base, and it's a very reactive base, but this substituent here is not. Now, for chlorine, that's not really a strong base to begin with, and obviously, if I were to draw this donating to there to give us a positive formal charge on chlorine, that's going to be far less stable than this is, but this is something that can contribute to resonance. I can even form a species like this and isolate it. I don't think you could ever isolate a compound that would have chlorine with a positive formal charge. Now, all I wanted to say about the structure of your leaving group is the role that the leaving group has in substitution and nucleophilic substitution reactions. Obviously, the better nucleophile, the better leaving group that we have, the more rapid the nucleophilic substitution reaction is going to take place. We've already done hundreds of examples of this in earlier chapters. The next thing that I wanted to go through is nomenclature, and it's kind of I guess redundant, and I think there's more important things worth noting, but I think you have to start somewhere. So the first thing that I want to talk about would be nomenclature of acid chlorides. So Just go ahead and branch this off here, just like when we talked about with any other type of nomenclature. We have nomenclature when we're dealing with a ring, and then we have nomenclature when we're dealing with a chain. So I'll start with a chain first because that just seems more prevalent in nature. Now, if you have a chain, or really with all of these species, you want to look at them in terms of, well, these are carboxylic acid derivatives. So they're derived from carboxylic acid. So I need to think of what the parent carboxylic acid would be. And so that's exactly what I'm going to do when I'm working with a chain. So I just simply find out the parent. I'm just going to write it out like that because that's the shorter way of naming the carboxylic acid. And then once I do that, once I've identified that, I simply, obviously this would remove the ending of ic. I'm going to remove the ic acid, and then I'm going to add chloride. Okay, so now I want to talk about a ring, and I'll give examples of each of these because that's really the only way to learn this stuff, is to give examples to do them by practice problems. But if we have something that's a ring, we do the exact same thing. We name ourselves our parent carboxylic acid. When we had talked about nomenclature of carboxylic acids, we simply remove the suffix of carboxylic acid. And after we've done that, we simply add the suffix of carbonyl chloride. Hopefully you can see that. So let's do some practice problems to show what I'm talking about. I'm going to switch colors for that. Okay, so see if you can name this compound. So the parent derivative of this species would have been a cyclohexane with a carboxylic acid attached to it. The parent name would be cyclohexane carboxylic acid. So all I have to do now is simply change to accommodate that it's an acid chloride. So I'm going to keep the cyclohexane attached to it for a final, I'll do that in gold just to show what I'm talking about. So I'm going to keep the cyclohexane. And this is so ugly. I hate this nomenclature, but I'm going to simply replace that with carbonyl chloride. So this would be named cyclohexane carbonyl chloride. Cyclohexane carbonyl chloride. All right, let's do another one. All right, so see if you can name this compound. Pause the video if you need to. So I want to know what the parent would be. I'm going to go ahead and number my carbon atoms. I'm going to go ahead and make sure that I am not missing anything. So I have a 4-carbon molecule here, and at carbon number 2, I have a methyl group sticking off of it. So I use the mnemonic here that means that this is a 4-carbon molecule. So I go, men eat pickled beets. That tells me that it is a butane because it's all single bonded there. At this carbon number 2, there's a methyl group. So if I were to list the parent name of this species, this would be a 2-methyl-butanoic acid. All I have to do is simply, like I said, remove the oic acid, and I'm going to simply replace that with onyl chloride. So the official name with this would be 2-methyl-butanyl chloride. All right, cool. Next thing I want to talk about would be nomenclature for anhydrides, and that's something that we really haven't, I guess, divulged into much details on, but if I were to give an abstract description of what these guys look like, you kind of start off with a species looking like this, and then you have 2 keto groups, I guess, attached to that. If this is, just know that this is a carboxylic acid derivative. Now, it depends on what the generalized structure is for your anhydride. If your anhydride is symmetric, because obviously we can't be talking about rings and chains here with something like this, or whether or not it is asymmetric. That's the determining factor in how you're going to name these compounds. So assuming that we have a symmetric anhydride, the first thing you're going to do is name the parent acid, and it's the exact same on either side because, well, yeah, it's symmetrical. And then we simply add the suffix of that should be anhydride. Don't know really how that escaped me. But anyways, you add the suffix of anhydride. Now, If it's an asymmetric anhydride, the first thing you want to do is alphabetize the names of your parent acids. After you do that, you're going to replace the word acid by anhydride. So we were simply the same here as over here. So we remove your acid, and we're going to replace that with anhydride. So let me show an example of what I'm talking about. So let's see what the name of this compound would be. Now, for some reason, acetic acid is simply the common name, kind of just dominates the IUPAC name. So I'm going to say this comes from acetic acid, and obviously that's A coming before B. And then if we have this right here, where did this come from? Well, let's see if we were to imagine with an RH group there attached to it. This would be benzoic acid. And so all I have to do is now I'm going to alphabetize my names, but I'm going to remove the acid and I'm going to add anhydride. So I simply call this, instead of saying that this is acetic benzoic acid, I say this is acetic benzoic anhydride. Acetic benzoic anhydride. Cool. So esters are made up of two parts. There's an acyl group and then an alkyl group. So with the acyl group, which as you can tell is the one with the carbonyl compound to this, you simply name the parent acid. And then the next thing you're going to do is name the alkyl group. So all you have to do with that is simply name that. And then this is going to take, remove the acid nomenclature. And in doing so, you simply add 8. Example of what I'm talking about for this. So see if you can name this compound, CH3C. Obviously we have an alkyl group and we have an alkyl group, and an acyl group. If I look at this, this is a 2-carbon species. I know that this came from acetic acid. Just to clarify what it is that I'm talking about this thing over here. That came from acetic acid. And then when I look at the alkyl group, well, this is just the alkyl group is an ethyl group. So it's an ethyl group. And when I put these two together, it will be known as ethyl acetate. And as you can, I don't think I designated these, but when you're naming these, obviously the order of it comes into play. Your alkyl group is always going to be first, and then your acyl group is always going to be second, as demonstrated by this example here. Okay, so for amides, the nomenclature is a little bit more tricky, I guess, or really, I think it's more mechanistically. There's two different categories of how you're going to name this. Is primary amides, and then there's secondary amides. So if it's a primary amide, all you have to do is remove the ic acid from your parent acid and simply add the phrase amide. Pretty straightforward. For secondary or tertiary, you have to identify your acyl and then your alkyl groups. For the acyl, you're simply going to name that the same way as you would a parent acid, removing the ic acid and adding the word amide to it. But part of what you're going to use is the in, and then whatever your in is the substituents that are attached to your nitrogen. And I can't write in italics, but you're supposed to designate that in italics to distinguish it from the phrase normal, and it's supposed to be bold and capitalized. So let's do an example of what I'm talking about. Okay, so for naming this compound, I'm going to go ahead and just follow along with my rules. I have my acyl group over here, and then I have my alkyl groups that are attached to my carbon atom. So the acyl group, the normal original name of this, the parent name of this acid would have been, if I were to just imagine changing this with an OH group, would have been benzoic acid. And my alkyl groups, have 2 methyl groups attached to it. So I have 2 methyls attached to it. So I have to designate each and every one of these with the substituent format of N. Just like as if you had 2 methyl groups at carbon 1 on a chain. I have to do the same thing here. So I'm going to label this as N because they're both attached to N. And I have 2 of them, so I'm going to say that this is dimethyl. Now I have the benzoic acid here, but I'm going to go ahead and remove the oic acid and replace that with amide. So and just like before, I don't think I designated this actually in colors, but alkyl group comes first in my lettering, and then the acyl group comes second in my lettering. And then for primaries, that's pretty straightforward. I'm not even going to bother doing an example for that. But what I'm going to use to name this is, so I have a benzoic acid here, but this comes first, so I'm going to go ahead and just kind of put him over here. So I'm going to name this species as N dimethyl benzylamide, or benzylamide if you'd like to think about it. Okay, see where that came from? So when we have a nitrile that exists as a substituent, we go ahead and just label that as a cyano group. That's nothing new for this. For the nitrile, all we have to do is simply number our longest chain and then add the word nitrile to the name of your chain. So